Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we're going to go over regression in large data sets. Specifically, we're going to take a look at the dataset large credit in your course document, Data Files, Chapter 4. There's a dataset called large credit that has about 5,000 rows of data, and we want to investigate a regression in large data sets in R. So the first thing I did here is to get my work directory, and I noticed that I'm reading off of documents, and I dropped my large credit.csv into the same work directory. Now I'm going to go ahead and read this file using read.csv command. After reading the data to make sure that it came properly to my console, I'm going to go ahead and get a head of the data that says there is account number, annual income, household size, years of post-high school education, hours per week watching television, and annual charges. These are related to credit card. Basically, we would be interested in predicting annual charges based on some of these variables. Now, another thing you can also do to make sure that the whole data came through to your console is get the dimension of the data, which is about 5,896 rows. If I execute data by itself, you see we have a lot of NAs toward the end. So the data set is about 5,000 when you look at it in Excel. However, after 5,000 rows, 5,000 all the way to 5,896, we have a lot of NAs. So what I can do to clean the data, I can say the data is equal to data from row 1 through 5,000, and I can get rid of everything else that I have in that data set. Now, if I look at the dimension of data, it's 5,000 rows and 6 columns. And if I look at the head of the data, I can see everything. Also, another thing I can do to clean this data set is to change the names of the columns. So I'm going to go ahead and do that using the names function. I call it account number. The second one is income. I shorten all these names so that everything is easily observable. And then I would say education. For the next one, I would say TV. And then the next one, I put charges. Now I changed the name of the headers to shorter version. If I execute this and look at the head of the data, it's much easier to see this data set. It's because condensed into a smaller portion of my screen. It's very easy to see it. If I execute the data, I can see the last few rows. There are all numbers and there is no NAs in them. So the benefit of changing names is just like a more compact form as opposed to your initial data set. What I want to do next is to basically create a linear regression model for this data set based on some of these variables. So I want to predict the charges based on income, household size, and education. So using these first three variables. Obviously, account number is not going to be a factor because it's just a number associated with each account to identify the person and their charges. However, is not a variable that would be significant in predicting the charges. So I'm going to create a linear model that in data set we want to predict charges, tilde, based on income, household size, and education. I really like the copy and paste as opposed to typing in because it prevents me from making mistakes and typos. I save this linear model in a variable called output, and I get the summary of the output so that I can see the result. Everything is pretty much significant. However, our adjusted R-square and R-square is pretty low. It means that these three variables are not capturing enough variability. However, if you look at the p-value of all these variables in addition to the model, you see that the model is highly significant. A reason for this is that because we have so much data, we have about 5,000 rows of data, that almost everything becomes significant. So that's one of the drawbacks of regression model on large data set, because typically everything becomes significant. So unless you have a rational behind predicting some variables based on some other predictors, you cannot include it in a linear model, because when you have a large data set, everything pretty much becomes significant. Now let's go ahead and add the other variables that we had. That was TV. If I run this, you see that everything becomes significant. Even TV is highly significant. However, your adjusted R-square hasn't increased much, so it's only increased 0.0032 units. So you see that by adding this variable, even though it's highly significant, your variability has not changed much. Therefore, unless you have a reasonable, rational behind including a variable in your regression model, you're not allowed to do so. That's why for larger data set, we prefer to use machine learning and other method of forecasting as opposed to regression. So now I want to show you how this regression model is sensitive to the sample size that we choose. If you choose a sample size of 50, this model is going to be completely different, and you're not going to see everything as highly significant. To do that, I'm going to go ahead and choose a random sample of 50 observations from this data set. The function that helps me to do that is called sample. So I say sample, choose a sample from 1 to 5,000. How many I want? 50. So in sample function, you define the range from 1 to 5,000, and you define how many you want. And I define that as IDX or index. So I want a sample of 50 observation from rows 1 through 5,000. So if I run this line, IDX creates 50 random numbers. Now, if I go ahead and choose those rows, basically in my data, I want to include the IDX rows and include all the columns. That's why I leave it empty. And we call this sample 1. So if I look at my sample 1, execute this, I only deal with only 50 rows of this data that are randomly selected from my data set. So for example, the random numbers we had 4,229. That means it goes to the rows 4,229 and bring everything in that row for us. Now I can use sample 1 to create my regression model. So I'm going to go ahead and copy these two lines over here. This time, instead of using data, I'm going to use sample 1, which is a sample of 50 rows of data, and execute this two line and look at the summary of my regression. As you see, this time intercept is no longer significant, and the household size is barely significant as at 0.05 level of significance. So you see that it's very close to 0.05, but still is less than 0.05, so it's significant at 95% level of confidence. However, your intercept must be dropped. So if I go ahead and drop the intercept by adding -1 to the model and execute this one more time, you see that this time everything is significant. And my model is significant. My adjusted R-square has gone significantly high. Previously it was about 40%. Now it's about 85%. We know that this is a little bit fake because when you remove an intercept from a regression model, we have an inflation in R-square. And the reason for that is our basis of comparison changes from the average line to the y=0, or basically x-axis. So that's why you see an inflation in the adjusted R-square. So if I run this process one more time, I'm going to get a different sample. So I'm going to keep repeating the sampling process and every time look at the output. Make sure that before you do this, you remove the -1 because we don't know if the intercept is significant or not. So I'm going to go ahead and run this one more time. If I take another sample of 50, you see the household size and education are no longer significant. Intercept is no longer significant. If I drop the intercept in this case and look at the result, now household size and education are not significant. I drop the household size and run the regression model again. Still education is not significant. And I remove it from the model and I look at the regression model and I see that only income is significant for the amount of charges that I have in my credit card. If I go back basically to initial model again and repeat the same process with another sample. So I'm going to go ahead and return back to initial model that we had with dataset sample, but this time I'm going to run it one more time to see another sample of data. So I'm going to go ahead and run this, and you see this time household is significant at 90% level of confidence. However, at 95% is not significant. Intercept is not, education is not. As you see, every time I run this, I get a different output. You see that for different samples, it seems like most of the time only income is the only significant variable. If you look at a sample of 50, in this example, you see household is also significant. Why so much variation and why so much difference? Because when you have a big data set, pretty much everything becomes significant. And you have to be very careful because in this case, you want to think through your predictor or predictive variables here and make sure that you include them if you have a rationale behind it. And you cannot just rely on the regression to tell you what is significant or not, because something that is not really an important factor can become significant. So what is the best way to deal with this? Best way typically is to put a part of your data set away for training and a part for testing. Basically, what I can do, I can take a sample of my data set, put half of it away for my training and another half for testing. And then, so develop my model based on half of my data set and use my regression model to predict the second half and see how good my regression model is for predicting a sample that hasn't been introduced to it in the first place. So let's go ahead and do that. The first thing is I'm going to divide this section. I want to use my data set, break it in two parts, training and testing, and then use the training to develop the model and test it on my test set and see how good it can predict the results. So to do that, first I'm going to use shuffling technique. So I'm going to shuffle my data, make sure that everything is randomly divided, and then choose rows 1 through 2,500 for training, 2,501 through 5,000 for testing. So to do that, I'm going to define IDX to be sample numbers, or basically you're generating random numbers from 1 through 5,000. So I'm creating 5,000 random numbers between 1 through 5,000, and I put replace false. It means that when you choose a number, you don't put it back in the bag again. Basically, if you chose a number, you're not going to be able to repeat it again. That way, we avoid generation of similar rows for the purpose of shuffling. So if I run this IDX and look at it, I have generated 5,000 random numbers from 1 through 5,000. So I exactly have 5,000 numbers here. And what I'm going to do, I'm going to say my data is equal to my data with those indexes. So the rows are shuffled now based on these IDX that I have generated. If you want to make sure that you're looking at the right data set, you can run the dim data to make sure that you have 5,000 rows. So I'm going to go ahead and say data is equal to the data where the rows are arranged based on these random order that we created here. So I'm going to execute that. Now I have a shuffled data set. After that, what I want to do is divide my data to training, which is going to be the first 2,500 rows. So it's going to be data 1 through 2,500, and we bring all the columns. That's why I leave it empty. And testing is going to be the second half of data, which is from 2,501 to 5,000. So that becomes my testing. So make sure that you change this to test. Now let's go ahead and execute that. Two lines, so we have train and test to make sure that they are right. So you can look at the head of train and also head of test. Make sure your data hasn't changed. So I'm going to change this to test. Also, another thing you can do, you get the dimension. Make sure that each of them is 2,500. I'm going to do that for both of them. I see everything is okay. Now I want to use the train to develop this regression model. So I'm just going to copy this on the top and change the data set to be my train data set. So now if I execute this and look at the summary of output, everything is pretty much significant. The R-square is not very strong, so that means there are variables that are important that we haven't included. Also, the total model is significant. So you have the p-value of the f-test that shows whether you have a regression model or not is less than 5%. If you assume that 5% is our level of significance, you have a regression model with all the variables being significant. But how good is this model in predicting a new data set, which is my test? We want to know in the test data set how good we can make the prediction. So remember, when you look at the head of the test set, we already have the charges. Now we want to use this model with these coefficients to make a prediction here. And then when we did that, we want to calculate some sort of sum square of errors and see how good this model has worked in terms of predicting these values. You can also take a look at the ANOVA table here. ANOVA of output is showing you that the sum square of residuals in this case is this value, 5.8 multiplied by e to the power of 10. So you want to know now how good this model is in terms of predicting your test set. So the function in R that allows you to make a prediction using your regression output is called predict, where you put the regression that you have created output here and the data set that you want to use for prediction here, which we call it test. So we put it in here and we use it for prediction. But let's save it in a variable called pred. So I'm going to execute it and then look at the head of the pred, because otherwise it's a little bit too big to take a look. So if I look at the prediction, for example, the first row is 2,850. You see the first row is related to 2,850. So if you look at that, the prediction related to that is equal to 9,227, while the charges are equal to 4,640. So how do I can use this prediction to calculate the errors? You can attach that prediction to your data set. So basically I can say the test data set, $pred is equal to prediction of output using the test data set. That way, if I look at the head of the test, prediction is attached here. I can attach now the residuals next to it and calculate how much error we have. We can calculate the sum square of errors in here, or minus square of errors in here. So let's go ahead and do that. I can calculate the residuals, or let's call it error, and we're going to attach it to dataset test. Error is equal to, we're going to have test charges minus test prediction. If I execute this line and look at the head of the test, you see that errors are generated now in here. Now if I want to calculate the sum square of errors, I have to add another variable, sum square of error, which is equal to the summation of test error. And that gives you the summation, but you want to square it. So first you square that and then you sum the squares this way. And if I look at the SSE, now I have this number. If you compare it, it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to be 5.8. E plus 10, that's the number that you get. If you look at the ANOVA of output, you got almost the same number in here. So this is a slightly bigger than that because it's 5.88. This is 5.85. So you get a slightly around the same amount of error that you have, but still you see that the sum square of error is really big because your R square is really low. So this model is not really a good model for predicting your future outcome, even though this SSE of your test is pretty much the same as your SSE of your training set. So the point was we developed a regression model over training set, use it to predict the value for the test set, because test set wasn't used to develop the model. We want to know how good the regression model is going to predict future outcomes that it's not been exposed to. So when you do that, you see that how much error you get. We calculated the sum square of error, and as you see, the sum square of error is pretty high. It's very relative, comparable to what you got for your sum square of errors from the training set. However, overall your R square is pretty low and you don't want to use it. So what is the point of this whole regression on large data set? Two things I want to show you. First, that unless you're sure of one variable, you don't include it, because if you include anything in a large data set, everything and anything becomes significant. For example, the hours of watching the TV might not necessarily have anything to do with charges, but if you put it in there, it's going to be significant. So unless you have some strong evidences, don't throw everything in the model because you're not sure of their actual correlation and relationship. Second is that if you have a large data set, another thing that you can do to make sure the model is good, look into dividing your data set in two parts, training and test set. Set up a regression model for training. Try to predict your test set and calculate some sum square of errors or min square of errors and compare it between the two models and see if your performance increases, decreases, or stays the same. For the most part, if the performance stays the same or gets better, it's good. But if the performance gets drastically lower, it's really bad. So in this case, the performance didn't change much. So it means that the model is performing as good on the test set as it was on the initial data set. But the model in the first place wasn't good to be used for future references because of its low R-square. However, if the model in the first place has a high R-square and you compared these sum and square of errors between the two models and you saw that they are not much different from each other, so maybe this is a good model because your performance hasn't declined significantly after using your regression model on your test set. All right, with this, our lesson has concluded. Please refer to your Blackboard for your assignments. Thank you.